Hi children and viewers. In previous video I explained about the Kirchhoff laws. What is Kirchhoff first law and what is Kirchhoff second law, and which sign convention rules we have to follow to explain the Kirchhoff first law and Kirchhoff second law. Clear? In this video I am going to explain one of the most important question for examination point of view, that is especially for IPE examination point of view. This is very important question. So, and the same concept is also taken as important for other competitive exams. That's why you have to watch the video very carefully with more attention. Got my point, children? So you have to watch the video without any skip. Today I am going to explain about the most important topic, that is Wheatstone bridge. Wheatstone bridge. So what is the Wheatstone bridge? So it is the device, or it is a one type of network that should be used to compare the resistors, compare the values of resistance, and by using it we will find out the unknown resistance in a circuit. So these are the main two applications of Wheatstone bridge. First thing is what? Wheatstone bridge can be used to compare the resistances of resistors. And next thing is what? By using it we can find out the unknown resistance value in a circuit. So here how the construction of Wheatstone bridge takes place and what way we will find out the unknown resistance value. So let us go for that. Without late I am going to start here. So on board one diagram it is said that will resembles the almost all Wheatstone bridge structure. Here this is the diagram, children. Today topic is Wheatstone bridge. Wheatstone bridge consists of four resistors of resistance values P, Q, R, S. So these four resistors should be arranged like this. So in between A and C a cell or battery should be connected. So that is simply about the construction of Wheatstone bridge. Okay children, so here you have to find out that here almost all four resistors are there. Here we are showing like this. That should be here, arrangement should be like this. Here we are simply showing this is the resistor P and this is the resistor Q and this is the resistor R and this is the resistor S. So this is the simply in this way four resistors should be arranged. Clear children? So in the diagram here we are having some like this A, B, C and D. Here that should be given to one cell. That should be given to one cell like this. This is the cell we are given. Okay children. So you have to observe now here the current is always moves from higher potential to the lower potential. The current is moving from higher potential to the lower potential. So children here, so the current is I coming like this. Now at this point here the current reaches how much it is I. At this point the current reaches the I, and now at this point again there are two paths. There are two paths. Clear? The current is splits into the two paths. That's why here the point A is taken as the junction. Similarly the current is going like through the resistor P and that should be reaches here. So and children, in between B and D here one galvanometer is connected. In between B and D one galvanometer is connected. Its resistance is G. So generally galvanometer can be used to find out the direction of current, at the same time strength of current up to 10 power of -9 amperes. So here in between B and D one galvanometer is connected. So children, here at the point A the current is I, and now there should be splits into the two paths. That's why I have taken this is the I1 and this is I2. Clear? and after that the I1 current is passed through the resistor of resistance B, and that should be reaches at this point B. So again that should be splits into two paths. S. So one is passes through the galvanometer and another is passes through the resistor Q. That's why here the current is again splits into two paths. That's why B also here one junction. So this is I1. From that B, now the amount of current that should be passes through the galvanometer should be taken as IZ. And this is again now here I am saying now this is I3. From the point B, the current is again going into two paths. One is through the galvanometer and one is through the resistor Q. Clear, children? So again the current is coming like this. Here I2 current and IZ current. That should be touches the point B, point D. So this is I2 and this is IZ. I2, IZ enter into the B, and now this I4. Here from that the I4 is leaving. The I4 is leaving. Clear? And again here the current coming through the resistor Q is I3. So here again at the point C, I3 and IQ are entered. From that again the current is leaving I. So here I3 entered and I4 entered. So at this point C, now here the current amount again coming, that is I. So children, the entire thing should be in diagram only. If you can understand the diagram, we can go for derivation. Very easiest derivation once you have to focus at the diagram. Clear, children? So children, here we have four resistors P, Q, R, S, and in between B and D one galvanometer is connected. In between A and C one cell is connected. Now once the cell is connected, the current is moving like this here. At the point I, the current is splits into I1 into I2. At the point A, the current I1 is splits into I is splits into I1 and I2. That's why here A is the junction. Again the I1 is passes through the P and reaches the point B. From that point the current is again splits into two paths, IZ and I3. IZ is the amount of current passed through the galvanometer and I3 is the amount of current passed through the resistor. And at the point D, the current I2 and IZ both can reach us. After that here again that should be passes through the like this. So at the D, I2 is entered, IZ is entered, and the amount of current which is going from the D simply that is I4. Now at the point C, the I3 is current entered and I4 also entered, and here from that C, I is coming outside. So this is the entire thing you have to remember. That much of important here. Once you can have idea about the all these things, what is I1, what is I3, and what is I4, and what is IZ. So then you can easily go for the derivation now, children. Children, what I explained again I am drawing here. While we are making the values or mentioning the values, you have to focus at the diagram. Children, again we have to watch. Wheatstone bridge consists of four resistors P, Q, R, S. So this is the cell. From that cell I amount of current is coming, and that should be reaches the point A. At the point I, the current entry is how much? I. Now that current is splits into two paths. At the point A, current is splits into two paths. Here this is I1 and this is I2. So I1 amount of current is passes through the P. At the point B again what you have to say? That should be splits into two parts, IZ and I3. IZ and I3. Got this point, children? Next thing is again here IZ is coming towards B and I2 is coming towards D. Again from I4 it is leaving as I4. Now this is I4 and this is I3. So again I3, I4 both are reaches the C. Then again the amount of current leaving is I. So again in this way the current I is coming. So this is the children the circuit of the Wheatstone bridge. Circuit of the Wheatstone bridge. Got children? Now you have to focus at the diagram. When you have to focus at the diagram, you came to know that in the diagram A, B, C, D, these four are the junctions. These four are the junctions. I already told you in the previous video what is meant by junction and how we can find out the amount of current at the junction. How we can find out that? By using the Kirchhoff first law. By using the Kirchhoff first law. So what is the Kirchhoff first law? According to Kirchhoff first law, the amount of current which is enter into the junction must be equal to the amount of current leaving the junction. The amount of current that should be enter into the junction is equal to the amount of current leaving the junction, or simply it is also stated as the algebraic sum of current at the junction should be taken as 0. So now we have to apply the junction law or junction rule or Kirchhoff first rule to the all the junctions. Clear? That's the first thing we have to go do. So children, we have to apply the Kirchhoff first law for the junctions A, B, C, D. Clear? What is the Kirchhoff first law? The amount of current enter into the junction is equal to the amount of current leaving the junction. Clear? That is going to be implemented for all the junctions in the diagram. Clear? Now, first thing is at junction A. At junction A. Simply I am writing at A. So children, you have to observe, this is the A. This is the point A. I am showing here. This is what? I. Clear? And the switch splits into how many types? How many ways? I1 and I2. So this is what? I1 and I2. Clear? I is equals to I1 plus I2. So what you have to children? The amount of current enter into the junction is what? I. Amount of current leaving junction is what? I1, I2. Clear? I1 is entered and I1, I2 are leaving the junction. So according to first law, what to write? Amount of current entering the junction equals to amount of current leaving the junction. That's why here children, you have to write here simply the amount of current is entered is what? I is equals to I1 plus I2. So this is the equation number 1 children. Clear? Now at the junction B. At junction B we are going to write. So at the junction B, children, how it is there? This is the junction B here, and simply I1 is entered and IZ and I3. What it is there, I am drawing separately here. Just what you have to observe, you have to observe it at the arrow marks. Based upon the arrow marks, you have to you may decide which is entered and which is leaving. I1 is here entered, IZ is leaving, and I3 also leaving. That's why here what you have to write children? At B, what do you write? I1 is entered, amount of current is what? I1, and leaving is what? I3 plus IZ. I3 plus IG. Now this is the equation number 2. Clear children? And next thing here at C, at the junction C, here, what is the junction children here? How it is? So this is like this. So what is that? This is I3 is entered and I4 also entered, I3 entered, I4 entered. This is the C. And what is leaving? I. So then what are the children? I3 plus amount of current entered, I3 plus I4 is equals to I. At the junction C, I3 is entered, I4 entered. Therefore, amount of current entered is what is? I3 plus I4. And leaving is what? I. So, I3 plus I4 is equals to I. So, this is at the junction C. Now, that should be taken as now here equation number 3. Clear? And now children, at the junction D now. So this is the junction D. At junction what we have? So here this is I2 is entered. I2 is entered and IG also entered. So this is the IZ. IZ means amount of current through the galvanometer. This is IZ and this is I2. IZ is entered and I2 is entered. And here I4 is leaving. Then what you are children? So at the junction D, I2 plus IZ. I2 plus IG is equals to I4. So now it is equation number 4. At the junction D, I2 plus IZ is equals to I4. Okay children. So these are the equations when we are applied Kirchhoff first law at the different junctions. Clear children. Now here we have to apply the Kirchhoff second law. Now we have to apply the Kirchhoff second law for the loops. So children, what is Kirchhoff second law? In a closed loop, the algebraic sum of potential should be 0. In a closed loop, the algebraic sum of potential should be taken as 0. That is the Kirchhoff second law. So in previous video, I clearly explained which rules we have to follow to apply the Kirchhoff second law for a closed loop. What are they? Simply, first we have to decide the direction of moving, either it is clockwise or anti-clockwise. And the potential values which are taken in the direction of current, the potential values which are taken in the direction of current, they can be taken as negative. The potentials which are taken in opposite direction of current, they can be taken as positive. Clear? So up to now you didn't see that video. Just first you go and watch that video. After that only you must watch this video. Clear? So now children, now we have to apply the Kirchhoff second law. Kirchhoff second law for the loop here. First we are taken two loops there here. First one is here A, B, C, D. It is the one closed loop. In that again, that is there are two parts. First one is I am going to take A, B, D, A. A, B, D, A. This is the one loop. Next one is B, C, D, B. This is the another loop. So first thing is here simply, now we have to apply the Kirchhoff second law. We have to apply the Kirchhoff second law for the loop. So here we are going to use now here for the loop A, B, D, A. A, B, D, A. So that means we are moving like this. We are moving in clockwise direction. We are decided we have to move in the clockwise direction. That is what A, B, D, A. Clear children? So I already told you children, while we are moving in the direction of current, the potential should be taken as negative. While we are moving in opposite direction of current, the potential is taken as positive. Clear? That's why children, here I1 amount of current is passes through the resistor of resistance P. So generally what we know, potential is what? V is equals to IR, Ohm's law. V is equals to IR. So product of current and resistance value gives the potential. Product of current and resistance, that is what gives potential. Like that, here I1 is there, I1 is the current and resistance is P. That's why here what is potential across this resistor? I1P. So here simply we are going that is I1P. So this I1P is the I1P. Clear? That is that I1P. I1P is the potential across the first resistor. So what I am telling, either it is taken as positive or negative. Here we are moving like this clockwise. That means we are moving in the direction of current. We are moving in the direction of current. Children, you have to observe now here. This is the clockwise direction. That means here we started here A, B, D, A. That means we are coming in the clockwise direction. And now we have to observe the direction of current also in the same direction. That means we are moving in the direction of current. That's why all the potential should be taken as negative here. That's why here minus I1P. This is what? Minus I1P. And children, now here current is IZ and resistance is G. Ig into G, Ig into G. That is what here potential across the galvanometer. That's why here I am writing now I G into G. Here G is what, children? G is nothing but here resistance of galvanometer. G is what? Resistance of the galvanometer. That's why here we will write product of current into V is equals to what it is? IR. Current into resistance. Current is what? IC. IC amount of current is passed through the galvanometer. And G is what? Resistance. Product of these two what we got? S. Potential minus Ig G. And now here, in this case, we are coming like this. So we are coming from A, B, D, A. We are coming like this, A, B, D to A. We are coming from D to A. But the current is here. We are coming from D to A like this. But the current is in opposite direction. Current is now here opposite direction. That's why here in this case the potential is what? Current is what? I2. And resistance is what? R. I2 into R. It is the potential across this third resistor. Clear? That's why, children, here in this case the potential is written as I2R. I2R. But it is moving in opposite direction of current. Because we are moving in opposite direction of current, that's why this potential value should be taken as plus. So again we reach the point A. So that's why here that is equals to 0. Now equation number 5. We apply, children. The algebraic sum of potentials in a loop is equals to 0. That is only Kirchhoff's second law. Kirchhoff's second law. So we are successfully applied for the loop A, B, D, A. Clear? Now in the same manner we have to apply the same second law of Kirchhoff to the loop. Now we are going to loop here B, C, D, B. B, C, D, B. Yes. B, C, D, B. So this is the loop. Second we are taken B, C, D, B. So this is the B. Like this. We are coming like this. Clear? Again we are selected clockwise direction. That is what? Clockwise direction, because we are shorted at the point B. We are coming like clock. B, C, D, B. So again same thing what I told you, explained now up to now. Same rules we have to follow. Here this is the resistor we have of resistance Q, and current is there I3. I3 is the current, Q is the resistance. Then potential what? According to this I3 into Q. So we are adding I3 into Q. Children, clear? I3 into Q. So now tell me, now we have to take plus or minus. I3Q is the potential. It is clear. What you have to take? It is plus or minus. We have to take the minus because we are moving in the direction of current. That's why it is minus I3Q. Minus I3Q. Clear, children? And after that, this one is finished. Now we are coming like this. We are coming from C to D. We are coming from C to D. We are moving in the direction of clockwise. So that's why we are coming from C to D, but the current is D to C. So the direction of moving of us and current both are in opposite direction. That's why here the potential what we take here I4, current into resistance what? S. I4 into S. I4 into S is the potential. Now it should be taken as positive. Here plus I4 into S. I4 into S. And next, children, here D to B we have to move. D to B we have to move, but the current is moving from B to D. B, C, D, B. This is our way of moving, path of moving. So we are moving from D to B, but the current is coming from B to D. That's why here the potential is what? Ig into G is the potential, and we are moving in opposite direction of current. That's why here the potential will be taken as positive. Ig into G is equals to 0. Now this is the equation number 6. So children, in this way we have to apply the Kirchhoff first law, Kirchhoff second law to that particular circuit of Wheatstone bridge. That's clear. Now children, here when the current is passes through the entire bridge, when the current is passes through the entire bridge, if there is no current is passes through the galvanometer, that means the current what we are supplying, that should be going like A, B, C and A, D, C. There is no current through the galvanometer. When the current is passes through this circuit, if there is no current passes through the galvanometer, then the bridge is said to be balanced. The Wheatstone bridge is said to be balanced. Clear, children? So when the bridge is said to be balanced, when the Wheatstone bridge is said to be balanced, that means what? When if there is no particular value of current passes through the galvanometer, simply the current passes through the galvanometer is 0. Clear? Then the bridge is said to be balanced. This point is important for 2 marks also. When the Wheatstone bridge is said to be balanced means when there is no current through the galvanometer, then the current should be 0. Then the bridge is said to be balanced. So here the galvanometer shows the strength of the current, at the same time it shows the null deflection. When the galvanometer shows null deflection, it is like a speedometer on our vehicle. In speedometer of our vehicle, if it shows 0 means what? The vehicle is at rest. Like that, in galvanometer, in that circuit, the galvanometer shows 0 means that is there is no current to the galvanometer. Then the bridge is said to be balanced. When there is no current through the galvanometer, the bridge is said to be balanced. Clear? And next thing here, so now I am writing here at the balancing condition. At the balancing condition. At the balancing condition. That means the bridge is balanced. That means what? There is no current through the galvanometer. No current through the galvanometer. IC is equals to 0. At the balancing condition, IC is equals to 0. Clear? When there is no current passes through the galvanometer, the bridge is said to be balanced. Clear? So that's why here, children, now we have to substitute the IC value in equation number 2 and equation number 4 and equation number 5 and 6. In which equations we have IC, there we have to substitute IC value is 0. So here, children, from this equation, here we are writing now from equation number 2. From equation number 2, what you write, children? I1 is equals to I3 plus IC. IC value is 0. That's why I am directly writing here I1 is equals to I3. What's that? I1 is equals to I3. From equation 2, I1 is equals to I3, children. Clear? And similarly, from equation number 4. So, from equation number 4, what do you write, children? What do you write? This is what? I2 plus IC is equals to I4. IC value is 0. Then I2 is equals to I4. I2 is equals to I4, children. Clear? When the bridge is said to be balanced, IC value is 0. Now we have to substitute the IC value in equation number 2 and 4. What do we get? In equation number 2 we get I1 is equals to I3 plus 0. That means I1 is equals to I3. And from equation number 4, I2 plus IC is equals to I4. Then IC value is 0. Then what do you get? I2 is equals to I4. In the same manner, children, from equation number 5. From equation number 5. So, children, from equation number 5, I am going to write here I1P minus IGG plus I2R is equals to 0. That means, children, here I am going to write, children, for our convenience, now I am just erasing only cell, so no need to confuse. Simply, we require some space. That's why here I am writing, this is IGG equals 0. So here, from equation number 5, from equation number 5, children. So what write? I1P minus Ig into G, minus Ig into G. Ig value is 0. That what you get, children? Plus I2 into R is equals to 0. Minus I1P minus 0 plus I2R. That means what, children? I1P is equals to I2R. So now this equation number I1P is equals to I2R. So equation number, this is 7. Okay children, next similarly here what we write from equation number 6, minus I3Q plus I4 into S plus Ig into G. That means what we get, minus I3Q plus I4 into S is equals to 0. So that is what children equation here. What from that what we get, simply we are write like this, I3Q is equals to I4S. Clear children? Minus I3Q plus I4S is equals to 0. From that what right, I3Q is equals to I4 into S. This is equation number 8. Equation number 8 children. So clear? So children, I am ready here from equation 2. From equation 2, what did children? I1 is equals to I3. I1 is equals to I3. So children, board is non-space, that's why I am taking a little bit gap. Look here children. So we have to apply the Ig is equals to 0. We have to substitute the Ig value into the equation number 5 and 6. Children, look at the equation where I am giving chalk. Minus I1P minus Ig plus I2R is equals to 0. Clear? Then is equals to 0. Here what I am telling, Ig value is 0. That means minus I1P minus 0 plus I2R. So we are writing only minus I1P plus I2R is equals to 0. From that what children, we are bringing I1P to that side. Then what we get, I1P is equals to I2R. Equation number 7. Next similarly from equation number 6, minus I3Q plus I4 into S plus Ig into G is equals to 0. Here Ig value is 0. That's why we get only these two terms. Minus I3Q plus I4 into S is equals to 0. Then from that equation what children, I3Q is equals to I4 into S. I4 into S. So children, now here we have to divide the equation number 7 and 8. We have to divide the equation number 7 and 8. 7 and 8. So equation number 1, equation number 2, equation number 3 and equation number 4. This is. So we have to divide these two equations. I1P by I3Q and I2R by I4S. So I1P by, we have divided equation number 7 and 8. What is equation number 7? I1P is equals to I2R. And what is equation number 8? I3Q is equals to I4S. So I1P by I3Q. I3Q is equals to I2R by, so I2R by I4S. So this is I1P by I3Q, I2R by I4S. So that is, we are divided like that. So children, from equation number 2 what we have, I1 is equals to I3. That means I1 is equals to I3. And from equation number 4 what you have, I2 is equals to I4. That means what we get, I1, I3 both are cancelled. Or I am writing one more equation here like this. Here I1P by this is what, I1P by I3Q. I1 is equals to I3. That's why here I am writing this is also I1Q. That is equals to I2R by I4S. So I2 is equals to I4. That's why here I am writing this is I2S. Then what do you get children? I1 cancel, I2 cancel. What do you get? P by Q is equals to R by S. P by Q is equals to R by S. So this is the final equation children. P by Q is equals to R by S. So children, so this is what we call, at the balancing condition we have formula is there. P by Q is equals to R by S. This is known as the Wheatstone-Bridge formula. P by Q is equals to R by S. In this formula, if we can know about the two values of resistor values, we will automatically find out the remaining two. We will compare the remaining two. Here for example, P by Q is equal to R by S. So if you know about P value, Q value, we will compare the R value and S value, because the ratio of these two gives the ratio of these two. And that way we will compare the resistor values. And next thing is P, Q, R. P, Q, R are the known values. Then we will find out the S value. That means P, Q, R values we can known. Then automatically we will find the S value. So in this way, children, the Wheatstone bridge can be used to find out the unknown resistance value of a particular resistor, and that can be used to compare the resistor values of a pair of resistances. Okay children, so see once again, very important topic, so that's why you have to see once again. So actually board is not spacious, that's why I am taking this much of risk. Okay children, here in that Wheatstone bridge, what is the Wheatstone bridge? It is the device that should be used to compare the resistance values of unknown resistors, pair of resistors, and that should be used to find out the value of unknown resistor. That's the main purpose. Next thing, here we have one diagram, it is there. So actually here we have one cell, it is there. I am showing like this here. Okay. So here this is the one resistor P. Wheatstone bridge consists of four resistor values of resistances P, Q, R, S. They should be arranged like this. In between B and D, we arrange some galvanometer. Its resistance value is G, and amount of current passed galvanometer is IZ. So I think so you may got full clarity about the how the current is splits and how many currents are going and how many resistors are there. You may got idea, I think so. Here from the cell, I current is entered into the junction A. In this diagram, in this circuit, we have four junctions A, B, C, D. Four junctions are there. In between A and C, we are giving the cell. In between B and D, we are giving galvanometer. At the junction A, the I amount of current is entered and I1 is leaving, I2 is leaving. That's why according to Kirchhoff first law, we will write I is equals to I1 plus I2. Equation number 1. Now at the junction B, I1 is entered and IZ and I3 is leaving. That's why according to Kirchhoff first law, what to write I1 is equals to I3 plus IZ. Now this is the equation number 2. And at the junction C, I3 is entered, I4 is entered, I is leaving. So I3 plus I4 is equals to I, equation number 3. Next at the junction D, I2 is entered and IZ is entered, I4 is leaving. Then what to write? At D, I2 plus IZ is equals to I4. So as first part of derivation, we have to apply the Kirchhoff first law to the four junctions. That is the first part of the derivation. And second one is, now we have to apply the Kirchhoff second law to the loops. First loop is what? A, B, D, A. This is the first loop. And second loop is what? B, C, D, B. B, C, D, B is the next loop. Clear? So these two are the loops. For that loops we have to apply the Kirchhoff second law. I already explained what is Kirchhoff second law. So for the loop A, B, D, A. So we are coming like this, A, B, D, A. I told you what's that? The potential which are in the direction of current, they should be taken as negative, and the currents which are in the opposite direction of current, they can be taken as positive. Here A1P, at the junction A, here our current is I1, I2. Here at the resistor current is what? I1, and resistor is what? P. So potential is what? I1P. So this I1P is negative because we are in the direction of current. And next here, the current is IZ, resistance is G, then potential is IZ into G. Again we are in the direction of S, current. That's why what is minus IZ into G. Now here from D to A we are moving, but the current is from A to D. That's why you both are in opposite direction. That's why the potential is I2R. That should be taken as positive. I1P minus IGG plus I2R is equals to 0. This is equation number 5. Similarly, we applied the second law to the B, C, D, B. Then what we get? We are adding minus I3Q plus I4S plus IG into G is equals to 0, because At this point, the potential is what? I3 into Q. We are in the direction of current. That's why here we'll write minus I3Q. And at this resistor, the current is I4. That should be moving in opposite direction to us. We are coming from C to D, and the current is moving from D to C. That's why here the potential is taken as positive I plus I4S. At the G, the potential is Ig into G. We are moving in the opposite direction of current. That's why here the potential is taken as Ig into G. Equation number 6. I3Q plus I4S plus Ig into G is equals to 0. That is equation number 6, children. So in this way, we have to apply the Kirchhoff's second law to the both loops as shown in figure. This is the second part. And third part here, we have to take the balancing condition. What is mean the balancing condition? When the current is passes through the circuit, if there is no current through the galvanometer, then the bridge is said to be balanced. If the current is passing through the entire circuit, but there is no current through the galvanometer, then the bridge is said to be balanced. At the balancing condition, there is no current through the galvanometer. That's why the current passes through the galvanometer should be taken as 0. Ig is equals to 0. So that is the main condition. At a balancing condition, Ig is equals to 0. What it is that? Ig is equals to 0. Now we have to apply the Ig value, substitute the Ig value in equation number 2 and in equation number 4 and equation number 5 and equation number 6. When we substitute equation number 2, what we get? I1 is equals to I3. I1 is equals to I3. From equation number 2, this is. And next, from equation number 4, I2 is equals to I4. Because here I1 is equals to I3 plus 0. That means I1 is equals to I3 from equation number 2. And from equation number 4, I2 plus 0 is equals to I4. That means what? I2 is equals to I4. And after that, we will apply same substitute the Ig value in equation number 5. Then what we get? Ig value is 0. That's why we will get only these two terms minus I1P plus I2R. From that, what we write? I1P is equals to I2R, equation number 7. Next, we have to substitute the Ig value in equation number 6. Ig is equals to 0. Then what we get, children? Minus I3Q plus I4 into S, that is equals to 0. Here what we get? I3 into Q is equals to I4 into S, equation number 8. So now we have to divide these two like this. I1P by I3Q and I2R by I4S. I2R by I4S. From equation number 2 and 4, we have I1 is equals to I3. These two are cancelled. From equation number 4, I2 is equals to I4. These two are cancelled. Then what do you get? I1 cancel, I2 cancel. P by Q is equals to R by S. So this is the balancing condition formula for Wheatstone bridge. P by Q is equals to R by S. By using that equation only, we will compare the unknown resistance values of two resistors. P by Q is equals to R by S. P and Q are the two known values. Then we will compare the R and S. In the same manner, when we know about the three resistor values, automatically we will find out the unknown resistance value of fourth one. So this is the children complete information about the Wheatstone bridge. I hope you understand. If you want to understand very clearly, just you can don't skip the video, and if you have any doubt, just go back and just watch the video clearly. So children, I hope you understand. So we will meet in the next video with some other interesting topic. Bye children, take care.